Welcome to the Deep Dive. Today, we're looking at a huge challenge in AI right now.
Yeah.
How do we get these amazing, billion parameter demos out of the lab?
And into real-world enterprise systems, right? Systems that need to be scalable, affordable, and, actually reliable.
Exactly. It feels like there's this hidden complexity.
Oh, absolutely. It's not just about the cool demo anymore. It's about building the infrastructure. Our sources today really dig into this. We're talking new protocols for AI agents to talk to each other and use tools.
Okay.
And then there's making models smarter with less data, which is crucial. And finally, the hardware side, the engineering tricks to make these monster models even affordable to run.
Got it. So our mission here is to unpack those standards, the training methods, and the optimization hacks that are shaping the next wave of AI. Let's frame it maybe around 3 pillars.
Sounds good.
How about the AI plumbing, then the data diet, and finally the hardware hacks?
Perfect. Let's start with the plumbing. Because honestly, without good communication standards, these multi-agent systems just become a mess. Super expensive, impossible to manage.
Right, and the core problem is that an agent needs to talk to lots of different things, doesn't it?
Exactly. It needs to connect to external tools, could be APIs, databases, whatever, but it also needs to, collaborate with other agents, maybe delegate tasks.
And our sources, especially Google, seem to be pointing towards 2 main ways to handle this: MCP for tools and A2A for agent chat.
That's the recommendation. MCP, the Model Context Protocol, is all about that agent-to-tool connection.
Okay, so MCP, is this basically like stopping the AI equivalent of spaghetti code when you hook up tools?
That's a great way to put it, yeah. MCP is designed as this universal open standard. It focuses just on agent-to-tool. Think about it before, if your LLM needed data from, say, your CRM, a pricing database, and maybe a weather API.
You'd be coding 3 different integrations and maintaining them.
Precisely. MCP acts like a buffer, a unifying layer. It gives you a standard way for the LLM and any tool to talk, with proper access controls built in. It's kind of like creating a standard REST API, but specifically for LLMs. It simplifies things massively.
Okay, that makes sense for one agent needing lots of tools. But what about agents working together? Like a sales agent asking a calendar agent to book a meeting. That needs agents talking directly, right? Peer-to-peer.
Exactly. And that's where A2A, agent-to-agent protocol, comes in. It's designed for that kind of collaboration and delegation between agents.
And how does that work in practice? If it's peer-to-peer, how does one agent even know another one exists or what it can do?
Good question. They can't rely on a central server for that, so A2A uses something called an agent card.
Like a business card?
Pretty much. It's a digital business card, usually in JSON format. When an agent joins the network, it broadcasts this card. It lists its ID, its skills, what inputs it needs, what outputs it provides.
So the sales agent can just, look around the network, find the scheduling agent's card, see it can book meetings, and then just hand off the task.
You got it. No human needed in the loop for that delegation. It's really key for building those complex, dynamic, multi-agent systems.
Okay, but things get even trickier when we zoom out, right? Thinking about this idea of an agentic web, millions of agents interacting globally, maybe without any central control. That sounds like it needs serious trust and security. Is that where ANP comes in?
Yes, ANP, the Agent Network Protocol. It's designed for that huge scale, that potential agentic web. And it operates from the start on the principle of least trust. Basically, assume you can't fully trust anyone else on the network.
So how do you establish identity then, in a totally decentralized way?
ANP leans on the W3C DID standard decentralized identifiers. This lets agents prove who they are without needing some big central authority, which is critical if you want this to work globally, across different platforms.
One thing that really jumped out at me from the sources on ANP was this human authorization method. For high-risk stuff, why bake human approval right into the protocol itself?
It's all about risk mitigation. Think about really critical actions in AI deciding to, say, liquidate a massive stock portfolio or transfer millions of dollars.
Yeah, you definitely don't want that happening automatically by mistake.
Absolutely not. So, for operations flagged as high risk, ANP mandates that a human has to explicitly sign off. The agent makes the request, the human confirms it, maybe using a secure key, biometrics, whatever, and only then does the agent get the final go-ahead signature to proceed. It keeps humans in control of the really important decisions.
Okay, so putting it all together,
Yeah.
we're probably going to see hybrid systems, right?
Yeah.
An agent might use MCP to grab data from internal systems, but then use A2A or maybe even ANP to delegate tasks out to other agents, maybe even agents outside the company.
Exactly. These protocols are complementary. They're the foundational pieces that let AI move beyond just chatting and start taking real, reliable actions in the world.
They enable actual automation, not just conversation.
Precisely.
Okay, communication sorted. But great plumbing doesn't help if the water is bad, right? The models themselves need to be smart. That brings us to pillar 2, the data diet. Feeding these massive models efficiently.
Yeah, and the whole industry's thinking has shifted here. For supervised fine-tuning SFT, everyone pretty much agrees now. Data quality beats quantity, hands down.
Okay.
The challenge is, how do you find those golden nuggets of data that actually boost performance and just ignore the rest? It's about separating the essence from the dross, as one source put it.
And this is where things get interesting with methods like grep. It seems almost counterintuitive the way it picks quality data.
It really is quite clever. The core idea behind DRAP is that fine-tuning works best when the data you use, specifically the responses in your training data, aligns with what the model already kind of expects, based on its pre-training.
Wait, hang on. So you're saying the best training answer isn't objectively the best? It's only the best for that specific model because the model is already sort of leaning that way?
That's the hypothesis, yeah. It's a shift away from just using external quality scores or human preference alone. Jameo works by getting multiple possible answers for an instruction. Then, it uses the base model itself to see which answer it finds most, well, probable or predictable.
How does it measure that predictability?
Technically, it looks for the response with the highest length normalized probability, or you could think of it as the lowest perplexity. Basically, which answer feels most natural to the model's existing wiring.
Wow, that sounds elegant. And computationally cheap.
Very efficient. It just needs one forward pass of the model to score the candidates, no complex training or optimization needed for the selection part itself, and the results. They're pretty striking.
Like how striking?
Well, one study showed Dree's selection achieved performance on par with a baseline that was trained on something like 4.5 times more data.
4.5 times. That's a huge efficiency gain. Massive cost savings on training, potentially.
Exactly. It's surgical precision instead of just throwing massive amounts of data at the problem.
But methods like GEP, they seem really tailored to the specific model you're fine-tuning. This brings up the trade-off the researchers mentioned, performance versus feasibility. Like, how easy is it to actually use?
That's the central tension, absolutely. You see it when you compare different data selection methods. Take IFD instruction following difficulty. It gets amazing efficiency gains.
Why is that?
Because it's deeply integrated with the model. It looks at internal things like loss values or features from inside the model architecture to figure out data quality. That tight coupling, that customization boosts performance.
So IFD is like getting a custom-built engine for your specific race car. Super fast, but you can't just swap it into another car.
Perfect analogy. Then at the other end, you've got something like alpagasis. Now, alpagasis often scores lower on pure efficiency metrics.
And why is that one less efficient?
Because it relies entirely on an external LLM, like asking ChatGPT to score the data quality. It doesn't know anything about the specific model you're trying to fine-tune.
Ah, okay. But I bet the upside is flexibility.
Exactly. Alpagasis has the highest feasibility. It's model agnostic, data set agnostic. You can pick it up and use it pretty much anywhere on any model without complex setup. So that's the dilemma, right?
Yeah.
Do you invest the effort to build a super customized, highly efficient pipeline like DRAP or IFD, or do you go for the easy-to-use, works-everywhere tool like alpagasis, even if it's a bit less performant?
And that choice probably dictates whether a company ends up with a few hyper-optimized AIs or maybe dozens of slightly less optimized but easier to deploy ones.
That's the engineering reality.
Okay, let's move to the final pillar then.
Yeah.
The hardware hacks. We've got the communication, we've got the smart data diet, but we still have these enormous models. How do we actually run them quickly and cheaply, especially for inference?
Yeah, inference costs can kill you. This is where engineers get really clever with optimization. One big area is parameter-efficient fine-tuning, or PEFT. And a standout technique here is LISA.
LISA. Okay, layer-wise importance, sampled atom W. That's a mouthful. How does it manage to save memory during training and beat established methods like LoRa in performance?
LISA's trick is about being selective during the optimization process. It basically freezes most of the middle layers in the large language model, just randomly picks a few to not freeze.
Okay.
Then it focuses all the training updates, all the memory-intensive work on the really critical layers, the input embedding layer at the start, the final language modeling head at the end, and just that small, randomly chosen handful of layers in between.
So it's like focusing your limited resources where they have the biggest impact, instead of tweaking parameters that maybe don't change the output much anyway.
That's the core insight, and the results are, well, kind of shocking sometimes. We're seeing data showing Lisa consistently beating Laura, often by like 10 to 35% on benchmarks like MT-Bench.
35%. For a company running models at scale, that's not trivial. That's real money on cloud bills.
Huge difference. And it's not just benchmark scores. The sources mentioned image generation examples. Laura fine-tuning often gives this sort of softer, maybe dreamlike quality, but the Lisa-tuned versions, they showed much more intricate detail, sharper clarity. You can actually see the difference in quality.
Wow. Okay, so Lisa is a powerful PEF technique, but it's part of a bigger toolkit for optimization, right? Like quantization.
Oh, definitely. Quantization is fundamental. Pretty much every major AI deployment uses it. It's about reducing the precision of the model's numbers, the weights, taking them from, say, 16-bit floating point down to 8-bit integers or even 4-bit.
Which saves memory and makes calculations faster.
Right. But the problem, especially with really big models, is that just naively chopping the precision can totally wreck the accuracy. You get these weird outlier features, usually in the activation layers, that have huge value.
And those outliers mess up the math when you go to lower precision.
Exactly. They dominate the calculations. So you need smarter techniques, like smooth quant.
Smooth quant. What's the trick there?
Smooth quant is clever because it finds those problematic outliers in the activations before you quantize, and then it mathematically shifts the difficulty, basically pushes that complexity out of the activations and into the weights layer instead.
And you do that offline, before deployment.
Yes, it's a pre-processing step. By smoothing out the activations, it lets you quantize both the weights and the activations down to lower precision, like INT8, without losing that crucial model accuracy. Huge win for hardware efficiency.
That's like mathematical judo, using the problem's weight against itself. Clever. And this works alongside other optimizations too, like pruning.
Absolutely. You've got pruning removing unimportant weights. And modern hardware like the NVIDIA A100 GPUs with their sparse tensor cores is actually designed for structured pruning, like NM sparsity.
Meaning you remove weights in a regular pattern the hardware understands.
Exactly, like guaranteeing that out of every block of 4 weights, 2 are 0. The hardware can process that much faster than random sparsity. And then there are architectural choices like mixture of experts, MoE.
Right, where you only use part of the model for any given input.
Yeah. Instead of one giant model, you have lots of smaller expert networks. When a query comes in, the system routes it to only the relevant experts. So you're only activating and computing on a fraction of the total parameters for any single inference task. Big savings on computation.
It really paints a picture, doesn't it? The whole stack, from picking training data to deploying on a GPU, is this intense balancing act. Software standards, super specialized training, and aggressive hardware optimization.
It really is. You can see how the future of reliable, scalable AI depends on getting all 3 layers right. You need those open communication standards like MCP and A2A for trust and collaboration. You need smart, model-specific data techniques like Grab to train effectively. And you absolutely need the hardware hacks like Lisa and SmoothQuant to make running these beasts practical.
So here's the final thought then, maybe the big tension to leave people with. We're seeing that the best performance, the biggest efficiency gains, often come from these really deep, customized methods like GRAC or IFD that know the model inside out.
Right, the bespoke approaches.
But at the same time, the things that enable broad collaboration and easy integration like MCP or A2A, they rely on being open, standardized, vendor agnostic. So how do organizations square that circle? How do they balance that need for absolute peak custom performance against the practical need for systems that are flexible, interoperable, easy to plug together?
That tension. Maximum efficiency versus maximum flexibility. That feels like it's going to be the defining challenge for AI architects over the next few years. Finding that sweet spot will be key.